Okay, so in the next short part here, we're just going to look quickly at a case study in formal verification. So one question that sort of you might be thinking about or comes up in discussion about these sorts of courses is, well, it's all very well proving simple theorems about, functions that we can write in a few lines, and maybe, as we'll see in a minute, proofs about simple programming languages that are very sort of restricted and so on. But does this actually work in practice, right? Can you actually prove real systems, that are non-trivial and so on? So CompCert is a example of doing just that. So basically it's a formally verified C compiler, and it used the proofs that verify it are all done in Coq, and the theorems that state what correctness means for a C compiler and all these sorts of things are defined in Coq and proven in Coq, and it's all open source, so you can go and find CompCert online and download it and use it as a C compiler, and you can have a look at the proofs and how they work. So they're really big, complex Coq developments, but to a reasonable degree of approximation, they use the same techniques pretty much that we're using in a lot of our work here, just much on a bigger scale. So if you go into week 7's topic on iLearn, you'll see a PDF here, which is a nice overview paper by the main guy who did the CompCert work. So there's lots of papers and a lot more detail, and since they did the original CompCert project, they've extended it in all sorts of ways to make it more, cover more different hardware targets and all this sort of stuff, add more features, and so on. So there's a lot more out there than is mentioned here, but this paper gives a really nice overview of the point of the project and how it works and all that sort of stuff. Now, I'm not going to go through the detail here. I'm just going to highlight a few things. So one of them is there's a discussion in the sort of section 2 here about what does it really mean for compilation to be trusted. If I have a compiler, what does it mean for it to be correct? Okay, and so they go through a few different possibilities here, but the one that they end up sort of using is this one up here, number 3. The down arrow you can think of as the specification, if you like. The source program S and the compile program C. So these are two programs written in different languages, and the downward arrow is a relation that sort of captures the execution or the evaluation behavior of those two things, right? So one might be a C program, this one might be an assembly language program, and we have a formal, precise definition of what it means to run these two programs. Now B is what they call a behavior. So that might be the program runs to the end and exits, or it might be it gets part of the way through and it core dumps because you access a bit of memory that you're not supposed to, or something like that. And it's got to capture everything that a program could be doing sort of along the way. So they restrict things to programs that don't go wrong, where wrong has a formal definition as well, which means things that just crash and so on aren't part of the exercise. So in this version of it, it's programs to get to the end, and you want the two things to have the same behavior. So in other words, if S has behavior B when run, then the compiled version of S has the same behavior. Okay, so there's a lot more to it than that, but that's sort of a high level view. The interesting thing about the structure of this is if I go down into the overview section, this is sort of a high level view of the actual compiler structure. And each of these boxes represents a language, right? So we start with a version of C. So this was called C Lite because they left out some features, many of which have been added in since this work was done. And the last one here is PPC, which is PowerPC assembly language code, right? So we're going from a high-level, pseudo high-level language C to an assembly language, low-level language. And all the other ones along the way are versions of sort of fairly traditional intermediate languages that compilers often use to make it's often easier to go translate in steps rather than try and go all the way to the final result in one step. So you can see there's a couple of different versions of C that are a bit simpler than C Lite. And then there's things like this one, which is a register transfer language, which is compiler terminology for a sort of a high-level version of assembler, where you sort of assume that you have lots of registers, and register allocation is saying, well, we need to accept that we don't have a finite number, we don't have an infinite number of registers, so we have to use a different version, and so on. The details of these aren't totally important. But the interesting part is that the proof works in a modular way. So if you think about, say, C Lite to C sharp minor, it's doing some things, right? So if you have a program written in C Lite, you feed it to this part, and you get a program written in C sharp minor. So if you have an idea of the semantics, the meaning of these two languages, and you have a definition of what these operations do, then you can write a theorem that says if the C Lite program behaves in a certain way, then applying, going across this arrow to the C sharp minor side and running that program, it'll behave in the same way or in a compatible way or whatever. And that just takes care of that one step. So if you do that thing essentially for all the steps, you get a bunch of lemmas, one for each of the, one for each of the transformation steps that the compiler is doing. And if you compose those theorems all together, you have a correctness thing that says the C Lite program and the PPC that results from compiling that program behave the same or in a compatible way. Okay, and that's sort of the high-level version of the this work, right? Obviously, there's a lot more to say about it than that. I encourage you to at least read this paper, or at least skim through and get a general feel for what they're doing and why they're doing it and all that sort of stuff. It's pretty clearly written, I think, and maybe you want to go and have a look at some other CompCert things, but it's probably the main example that people point to at the moment of a significant real-world verification task that's using the sorts of tools that we're using in COMP7010. Okay, we'll stop there. I'll pick up with the first part of IMP in the next part.